Hello, everyone, and welcome to our first video on Unit 1.7, which is the graphs of functions and piecewise functions. Though we should probably call this the properties of graphs of functions, but I digress. So we'll start with the properties. And in order to do that, we'll start with the first definition 1.7.1. Let f be some function defined on an interval a comma b. The function is said to be increasing on that interval if f of x sub 1 is less than f of x sub 2 for all x sub 1 less than x sub 2 in the interval. Now, that's a very mathy definition, and it's best seen visually what's really happening. So, for all x1 less than x2 in the interval. So, this would be your x1, and this would be your x sub 2, right? This would tell us that x sub 1 is less than x sub 2. Corresponding, like in correspondence with this, this value in blue is f of x sub 1, and this value in red is f of x sub 2. And you see that f of x sub 1 is less than f of x sub 2. And so that is what the definition is trying to describe via English instead of a picture. And then intuitively, you can think of it as the person is walking uphill. You're increasing if your person is walking uphill from left to right. Similarly, a function is said to be decreasing on a comma b if f of x sub 1 is greater than f of x sub 2 for all x sub 1 less than x sub 2. So everything's the same except for the decreasing and then the sign, like the direction of the inequality. So in this example, once again, we've got x sub 1. So this is f of x sub 1. And then x sub 2 right here, and this is f of x sub 2. And you see that f of x sub 1 is larger than f of x sub 2. And so that's the pictorial representation. And then intuitively, you can think of it as a person going down. So person going downhill. And the last little subpart of this definition is that a function is said to be constant on an interval a, b, if f of x sub 1 is equal to f of x sub 2 for all x sub 1 less than x sub 2 in the interval. So, once again, you have your x sub 1 and your x sub 2, and you'll notice that f of x sub 1 is equal to f of x sub 2. You're constant if you get the same value regardless. And so your person, if you were to draw them, they are just walking on a straight line. On a flat plane. So you have a couple of these problems. You might see them in your homework, or you might see them written elsewhere. And I'm going to call this a problematic example. And I'll explain why on the next page. The graph G is given below with the points A through E, A, B, C, D, E. Determine where G is increasing, decreasing, or constant. So if we look from A to B, we'd see that we're going uphill, which means that we're increasing. From B to C, we are constant because we're walking on flat ground. From C to D, we are decreasing because we're going downhill. And then from D to E, we are increasing because we're walking uphill. So that's the answer to that. But why is it problematic? This is a great question. So the thing is, we typically want intervals. I'm going to capitalize this. Of x. So intervals of x of increase slash decrease slash constantness. We want the intervals on which the function is increasing. We want the x values on which it's increasing or decreasing or constant. As such, it doesn't make sense to talk about points. So I like this example as a situation of trying to explain to you, like, okay, so looking at like where you're trying to find increasing and decreasing is looking at the the pieces where you're walking uphill, downhill, and so on and so forth. But it's much more useful mathematically later on, especially later on in your mathematical career, to talk about them as intervals of increase and decrease. So intervals of x. So when we're looking for places where a function's increasing, decreasing, and constant, we're looking at the graph itself, and then we're trying to determine the x values for where it's increasing or decreasing. So for increasing, I'm going to highlight these. Let's make increasing, I don't know, increasing feels like it should be red. So this is the improved example 1.7.1. Decreasing sounds like a blue concept, and constant sounds like a green concept. So I'm going to kind of highlight all the places that I see where the function's walking up a hill. Now, we've already done this, but that's going to be from A to B and from D to E. So it should be increasing from, if you look at the graph, now I've kind of hidden it, but the x values where you're increasing is from -5 to -3. Those are the x values on which your function is increasing, and then from 4 to 6. So we'll write those with a union symbol. So -5 to -3 unioned with from 4 to 6. That's where the function's increasing. Now, some places will, right now, we might write it with a union symbol. Other textbooks, so I might even just say or -5 comma -3 comma 4 comma 6. Some textbooks like to use a comma. This is kind of a heated debate when it comes to mathematics education, which one should be which one should be used. Should a union be used, or should a comma be used? And I believe, at least in the calculus community, the comma has been adopted as the correct choice, but either way should be acceptable. And if this ever happens and you make a mistake, let me know, like based on what the computer wants, and let me know, and I will correct it for you. Anyways, back onto it. Decreasing is where the function's walking downhill, which we already saw was from C to D. There. And so we're looking for the x values. So that's going to be from from +1 to 4. So 1 to 4. And then constant, we're looking for where the function is flat, which should be right here from B to C. And that's from x equals -3 to x equals 1. So from -3 to +1. Now, you might be asking yourself, Phil, why don't we put the endpoints on there? Now, some textbooks might. Some textbooks might say that the interval of decrease should be, don't write this down because I disagree with it. Some textbooks will say that it should be including the endpoints. However, it doesn't really make sense based on the definition to say that you're increasing at 4 when you can't check any number to the right of it. The whole point of the interval, like of the definition, is that I can pick any 2 points, and as long as I've picked 2 points, one being less than the other, it should be the case that the f of x sub 1 is either less than f of x sub 2 or vice versa. But if one of your, like, if you include the endpoint on it, then you can't find anything to the right of it. So I don't really agree with it, but some textbooks will write it that way. Ours should write it with parentheses. Anyways, and then we'll do example 1.7.2, which is the graph of h is given below. Answer the following questions. Just a little bit of review. Never hurts to do a little bit of practice. The domain and range of h. So remember, the domain is all the x values that get attained by points on your graph. So for example, -8 is not in our domain because there's no point on our graph that has an x value of -8. -7 is not in it because it's an open circle, but it's where we start. So from -7 all the way to +8, but including +8 is our domain. And including 8. And our range is done similarly. We go from most negative to most positive. So we go from down up, and the first y value that doesn't get attained but is a placeholder is -4, and then all the way up until 5, and including 5 because it's a solid dot. So our range is parenthesis -4 up to +5 and including it. Another reminder about function notation, what it means. So does h of 1 equal -2? Well, if h of 1 equaled -2, that would mean that the point 1 comma -2 is on the graph, which it is. So yes, because 1 comma -2 is on the graph. And that's my theorem from way back when, that a comma b is on the graph if and only if f of a is equal to b. It's very, very important when you're with your understanding of graphs. But now we'll move on to the actual stuff from this course, from this section rather. Increasing, decreasing, and constant. We'll just look at our graph to figure these things out. So increasing, that would be here. You're walking uphill there, and here until 4, and then past 6. So we have 3 intervals of increase. So increasing from -7 to -3. So that, remember, that's not a point. That's not the point -7, 3. That's the interval. That's the x interval, -7 to -3, because that's where we're increasing from in terms of x. We start increasing, our function starts increasing at x equals -7 and stops increasing at -3. Similarly, from 1 to 4. And similarly, from 6 to 8. Or once again, these could be replaced with commas. However you want to do it is fine with me. Just make sure that with the homework system in question that you stay consistent with what they want. If they want commas, use commas. If they want unions, use unions. Decreasing, this function only has one interval of decrease right here from x equals -3 to +1. And it only has one interval of being constant, which is from 4 to 6. And the last question, because I always think this one's kind of silly and it throws students for a loop at first, is find some ridiculous point. Now, it looks like it should be, well, Phil, I don't have the equation of this function. How could I plug in this value? And that's not like a nice number, so I can't like find it on the graph. But you have to remember that since h is constant, on 4 comma 6, h of 4.37 6895 is equal to 1. So it's trying to scare you by putting this really, really obnoxious decimal number out at you. But the key thing is, so 4.376895 is roughly about there. And so we're looking for the y value because we're looking for the function value. And since this is a constant curve, that's just going to be a y value of 1. And that's why the function equals 1 there. I could have just as easily asked you to find h of 4.8765444, whatever I may be, like any number of decimal numbers. As long as it's a number between 4 and 6, the value was going to be 1. Next, on to the other subsection of properties of functions. Definition 1.7.2 says let f be a function. Then the function is said to have a relative maximum at x equals a if there exists at least one open interval around x equals a such that f of a is greater than or equal to f of x for all x inside the interval. So just to get off my, I'll get off my soapbox in a second. I don't necessarily agree perfectly with this definition. I feel like it should be a strict inequality, but many textbooks will just, most textbooks do this. If you're curious as to why I don't like it that much, please feel free to talk to me. I'll bore you to death. But in the meantime, let's actually just stick with the definition that we're working with. So, intuitively, it's the person's at the top of a hill. So let's look at so this right here, that is A, and then this would be f of A. And so we know a point is a relative maximum if there exists some open interval. Now, you could have multiple, but you can just pick an open interval. That's an open interval around A. Around A. And if you look at the y values on that piece, you'll see that all of them are below our point. You move a little bit to the right of A and you get a value. It's very, very close to it, but it is still below f of A. So like if this is A, like if this is B, f of B is still below f of A. So intuitively, you got a person right here, and the person is the top of a hill. Person at top of a hill. That's where you have a relative maximum. Similarly, a function is said to have a relative minimum at x equals a if there exists at least one open interval around x equals a such that f of a is less than or equal to f of x for all x in the interval. So once again, that's the value f of a right there. And so if I can pick any open interval, like I could pick this big of an open interval if I wanted to, all I need to do is just find at least one. So tradition to try and make it small. And you'll see that on this piece, all the y values, I meant to write this. Sorry. All y values of the points are less than f of a. And then similarly, all y values of points are greater than f of a. And so if you're looking at it intuitively, and you're trying to think of it in terms of a person, the person's at the bottom of a valley. Person is at the bottom of a valley. So a little bit of jargon then, because this is important. Sadly, it's important. So f of a, let me zoom in just a smidgen to make my handwriting better. F of a is the relative max slash min value. And it occurs at x equals a. The point, the relative max slash min is the point a comma f of a. So this is something that when you say that the relative maximum value, like the relative maximum is a coordinate point, the value is the y value, and where it occurs is the x value. So you'll see that sometimes mentioned on like they just want the relative maximum value, and then they want to know where it occurs. The point is the actual relative maximum or minimum. And I'm getting sidetracked. Anyways, the second bullet point is that the plural of relative maxes and mins is relative extrema. So sometimes you'll see people mention this. They'll say find the relative extrema. That means find the relative maximums and relative minimums. So if you see that in a textbook, that's what they mean. Or a teacher says that or something. They mean the relative maximums and minimums. Now, one last thing that I meant to add a bullet point here, so we'll just add an extra one, is that some textbooks say local instead of relative? Just depends on the textbook, but some places will say a local max or a local min instead of a relative max or a relative min. And I don't have time to go over it, and it's not necessary for our course, but there are such things called absolute extrema, so absolute maximums and absolute minimums, but that usually gets touched on later on in your mathematical career. Anyways, here's an example of just kind of digesting all this stuff. So, and digesting the jargon. So the relative maximum, I'm gonna put a red box around it, a red highlighted box around it. That, and I'm gonna duplicate it, and I'm gonna put this for the relative minimum. The relative minimum I'm gonna do in purple. Style. There we go, purple. All right. So for the relative maximum, that's where we're at the top of a hill, and that would be precisely right there. And so the relative maximum value is 2, and it occurs at x equals -2. The relative maximum in question is the point -2 comma 2. That's the jargon at its core. Similarly, the relative minimum value is where at the bottom of a valley, which is right there. This function only has one relative maximum and one relative minimum. And so the relative minimum value is -4, and it occurs at x equals 1. So the relative minimum is the point 1 comma -4, x comma y. So that's just the jargon in action. So let's look at an actual example of multiple ones that we can do. So example 1.7.3, find the relative extrema of this function, of these functions. So you can color code them if you want. I'm going to make all my relative maxes in red and my relative minimums in blue. Or let's do purple since the curve is blue. So for this first one, we're looking for the tops of valleys, tops of hills right there and there. So the relative maximums are the points, -4 comma -1 and 0 comma 3. And then the relative minimums of this graph will be the bottoms of valleys, which are at -2 comma -3 and 3 comma 0. So this function had 2 relative maxes, 2 relative minimums. Now for this next one, it's a parabola. It looks like it's just going to be x squared that's been shifted to the left 2 units and down 4 units, but regardless, this curve never has a top of a hill. So there are no relative maximums. So NA, or none. So most places say none, but NA is also sufficient. Relative minimums, there is one right there at -2 comma -4. So just once again with the jargon, that's saying that it has a relative minimum value of -4, and it occurs at x equals -2. And this last graph, I forgot to add arrows to it, but oh well. So this curve right here, there are no hills and there are no valleys. So this is a curve that has no relative extrema. It has no relative max and no relative min. And that's that. All right, and then we'll go on to the last problem for this video, which is example 1.7.4, which once again is going to do a little bit of review, but also do some more stuff. So the domain and range. So notice that this is an arrow pointing downwards. So this goes on and on forever. So the domain is all the x values that get attained by points on our graph. So we'll start at -7 and go on to positive infinity. But we cannot include 7 because the circle is basically a placeholder. And then the range, since this goes down and down forever, there, like if I look at like -10 billion, there is going to be a point on the graph that has a y value of -10 billion. It goes all the way up, up and up and up until 5. So the range is -infinity up until 5, but not including it because we have an open circle there. Then increasing and decreasing and stuff. So let's color code that. Increasing and doing in red, decreasing in blue, and constant in green. So increasing would be from -4 to -1, and then from 1 all the way up to 4. So let's write those down. So increasing from x equals -4 to x equals -1. So the interval parenthesis -4 to comma -1. And then from 1 to 4, +1 to 4. Decreasing is going to be where it's going downhill, which will be at the start all the way up until 4, and then between -1 and +1, and then on forever. So it's decreasing from parenthesis -7 to -4, then from -1 to 1. Oh, I should be using union symbols, but commas are all, sorry. I'm used to doing commas because I teach a lot of calculus, but either way, should be fine. And then from 4 to positive infinity. And then constant, there are no intervals of constantness. It's never flat. Now, here's a fun question that I like, and I meant to ask it sooner, but I think it's very good. Determine the intervals on which f of x is less than 0. So let's break that down in case you don't see what that means. This means we like the y values are less than 0. Because if f of x is less than 0, you're saying your function values need to be less than 0. And the function value is synonymous with the y value. So if you're looking at a graph, down from here below, this is where f of x is less than 0, because that's where you'll have negative y values. And then from the x-axis and up, that's where f of x is going to be positive, because that's where you're above the x-axis. That's where your y values are positive. And then, of course, at 0, this is where f of x is equal to 0. So if I'm trying to find where f of x is less than 0, I just need to look for all the x values on which the function is below the x-axis. So that starts at -6. We're below the x-axis from -6 all the way up until x equals 3. And then also from 6 onwards. So we're negative. Our function is negative from -6 to 3. And then also, let's use a union symbol. And then from +6 to infinity. Because after 6, it just keeps going down and down and down forever. And now we'll find relative extrema, the actual thing in question, but it was good to do some practice. We'll do relative extrema in red and relative minima in purple just to stay consistent. So relative maxes are at the tops of hills. So right there and right there. So that's a relative max at -1, -1, and a relative max at 4, 2. And then a relative minimum, there's 2 of them, one right there at -4, -4, and one at 1, -3. So -4, -4, and then 1, -3. And that will do it for this video. In the next one, we'll talk about piecewise functions, and I'll see you there.